So now let's look at how the principle of virtual world can be used to help us work out the stiffness matrix element that we need in finite element analysis. So the derivation will be a bit long, but we just want to demonstrate you the basic principles behind. Okay, so we know that the principle of virtual world says, so let's just bring that back. Principle of virtual world says the internal energy, right, is minus the external energy equal to 0, right? So first of all, let's look at the internal energy. No energy. So imagine we have, what we are dealing with is a structure where we have some volume omega and some surface gamma. So this is continue on piece of a body, right? The internal energy is kind of easy because we have up here sigma and epsilon. So basically is the stress times strain, right? But to make it completely general, we do that as the integral over the whole volume times the strain, in this case is delta epsilon t, times the stress, and integrated over the whole volume, right? So this is the internal energy being stored by the body if it undergoes some deformation, right? On the other hand, we also have external energy, Wx. Now in this case, we will have two contributions. One is the forces that acting on the body for the whole volume. So in this case, we will still have some integral over the volume element of the body, right? And we'll also have forces that acting along the surface. So that will cause a deformation along the tangent to the surface. So that's a gamma, d gamma. So we will have a volume, and we will have something for the surface, right? Now let's say for the volume, we will have some sort of deformation. In this case, they are both written as du, delta u, right? And then we will have B, that is the volume force, so in this case this is B, and we'll have a surface force that is T. So it's quite straightforward. They are all basically just stress times strain, right? So that's what we try to achieve. Now if you do the principle of virtual work, you basically bring these two expressions together. Now what you're looking at is basically this guy, delta epsilon t sigma the omega minus the sum of omega du t times b d omega plus gamma dut times t d gamma equal to 0. So what you can think of is basically you have some external forces that have down to virtually displace the body to a new shape by this dashed line. So you have a deformation. So this is not so. So you have some sort of deformation here, which is delta U. Okay, and this delta U is being acted as a result of this B force and this T force, right? This the volume and surface forces. Now, this is the general equation for that underpins the principle of virtual work. So before we move on to manipulate this equation further, just want to highlight what we try to achieve here. What we try to achieve, right? We need to stick to the main goal that we try to achieve, so we don't get lost in the actual mathematical derivation of the whole thing. So we want to eventually, as we showed in the previous slide, the whole finite element analysis broke down to the equation of k times some sort of displacement A or deformation A equal to some external forces, right? So we want to manipulate this long integral equation into this form such that we come up with a general equation that allows us to compute K for an arbitrary finite element, right? So that's what we're trying to achieve. So let's see how we can do that. There are three key substitution we need to do to achieve this goal, and which I will show in this video. So the first of all, this is, if you want to go back to slides about 22 to 23, we introduce this idea of shape function. So that basically says the deformation of the whole body, or deformation of a body with multiple nodes, equal to the sum of the displacement at each node times something called the shape function. Let's go back to the recording bit. Okay, so this n is our shape function. So what does this shape function do? Where's my recording things gone? Okay. There you go. Let's bring back. Right, here it is. So what does this shape function do? So imagine you have something along the x-axis. So you have a bar element or a truss element with two nodes, 1 and 2, and you have a displacement at each node, A1 and A2. Now, because this is a continuous body, what happens is that when these two nodes start to move, it will start to move everything in between. Right? So you will start to have some displacements in all the points in between. So in order to work out what's the displacement at any arbitrary point x between these two nodes, this shape function basically allows you to interpolate the displacement from point 8 and point 2 to the middle point here, governed by the position x. And we'll show later how this thing works in real cases. So that's the first thing. Okay, we have this shape function. Now if we write this back into matrix form, what this basically is simply n dot a, right? And also to just make you to remember, what we can do now is plot this delta u, right? Plot this expression for u back to everything that got u here. So that gives us what? The first term is basically the same, right? And then we'll have the second term, which is now delta n dot a transpose times b the omega plus gamma delta n dot a t b, sorry, this is t the gamma equal to 0, and all we have done is basically this bit here and this bit here, right? So if you expand that, now it's a bit of mess, but as shown on the slide, in your lecture slide, this gives you this expression here, right? Minus, okay, move this further up a bit, gamma delta a times n transpose b the omega plus gamma delta a times n transpose t the gamma equal to 0. Okay, so what we need here later is to cancel out this delta a. So how do we do that? We need to introduce two other expressions, which we'll go into a bit more detail later. So this is number 2. We have an expression for strain where sigma equal to, or the epsilon equal to a matrix X times the shape function n a, which we can group the s dot n together later and get a new matrix b dot a. Right? The meaning of that, or how do we calculate these things, will be appearance a bit later. So here we have first the strain equal to b dot a, and then we have the stress is basically sigma, and it's related to the strain by a matrix called D, which is D dot epsilon, which is D dot B dot A. So we have this D here. The meaning of this will be appearance later. So these are the things that allow us to do this time transformation. So if we plot 2 and 3 into this bit there, that will allow us to come up with an expression that look like this. The first term now become what? Delta A times B transpose times D dot B d omega times A, right, equals, minus, we basically take the rest here, times n t b d omega plus gamma delta A and t d gamma equal to 0. Okay, now why we need that? So it turns out that first of all these three terms has this delta A there, so we can basically cancel that one out. So we move that one away, and that one away. And what do we left? We left with something times A minus, as I said before, this whole bunch is our external forces. So we have end up with an expression that look like this. Right? So we have integral of omega B transpose dot D dot B d omega times A equal to some external force, right? And what does this tells me? This tells me that, okay, my stiffness matrix in general can be calculated as K equal to the integral over the volume B transpose dot D dot B d omega. So that has come to the point to help us identify how to work out the stiffness matrix for finite element analysis. Now the thing is, how do we put this thing together for real system. So I'll jump ahead a little bit to highlight what's the step to work out steps to work out K from expression A. Right, so this is important, which we need to remember this. I would recommend you to actually write this down on a piece of paper before you go follow the subsequent part of the lecture notes. So first of all, we will need to work out the shape function n, which generally is a matrix for our system. Now this is because B is basically S dot n, right? So we need to work out the n based on the shape of the element, okay? Now, because you see here with no n, we still need s. So we also need to know what s is. Now, as shown in your lecture slide 72, the s is basically what we call a differential operator. And is of this form, dx d by dx 0 d by dy dx d by dx d by dy. So and people say, where does this come from? Okay, now where does this come from? So if you go to slide 72, I'll show you how to use this differential operator later, but just bear in mind that S is basically of this form for two-dimensional cases. So basically, if you think about this, what you can say is that the epsilon, the strain, is related to what? The strain along the x direction, right? The strain along the y direction, and in case of a, for example, let's bring that back. Right, so if you have a square element which will have x and y, so you will have a deformation along x, epsilon x, epsilon y, but it can also deform in this way, right? Because you know that a square is not mechanically rigid, they can deform diagonally, so you will have also a contribution from the cos term xy. So that's in general what you have for the strain in the system, right? And what this really is basically the changing length along x, so du by dx, du y by dy plus dux dy plus dux by dx plus dy by dy. Right? And this thing need to operate on what? And this can be extracted or written out in the operator form as d by dx 0 d 0 d by dy d by dx d by dy times u of x and u of y. And this is basically the S operator, right? That's basically an operator to work out the strain in the system. And then finally, let's try to bring this one. My iPad is not so responsive. So finally we have the stresses. Right? What we need that is basically the stress. Again, we have three components in the 2D system. We have the stress along x, stress along y, and stress along xy direction is equal to this D matrix, which is up here, times the corresponding strain, epsilon x, epsilon y, and gamma xy. Now, for the isotropic material, that means we have a uniformly distributed system. We can work out this D matrix from the Young's modulus, which is the Young's modulus, and the V, which is its Poisson ratio. And as shown in your slide, right, as shown in slides 74, this D matrix is given by E over 1 minus V squared. And remember, D must be a 3 by 3 matrix because it is linked a 1 by 3 column vector to a 1 by 3 column vector. So in this case, it look like this: 1 mu 0 mu 1 0 0 0 1 minus mu over 2. Right, this is something is based on the mechanics of the material, okay, which we're not going into too much detail how to derive that. So with this three information, so let's highlight what do we need. First of all, the shape function n, which will show a few more examples how to work that out for different type of elements. And then is the S operator. This is also given, and we'll also show you how this thing actually works later, right? And finally is this D matrix, right? With all these three things, we can work out here the stiffness matrix that's derived from the principles of virtual world. We'll show that for some real example in the next video.